Hello everyone, welcome to another episode of Math-321. So today we're going to finish up Investigation 30, which is homomorphisms and isomorphism theorems. And we're going to start into Investigation 31, the fundamental theorem of finite abelian groups. Okay, so last time we did the first isomorphism theorem for groups, and now we're going to get into the second isomorphism theorem. So there's a couple of results that we need to use here. So first of all, let G be a group, and let K and N be subgroups of G. Then K intersect N, so that's the overlapping parts of K and N, is also a subgroup of G. Furthermore, if N is a normal subgroup of G, then the set Kn, which is just the product of all the elements in K and N, that is also a subgroup of G. So the next activity is going to illustrate this theorem. Okay, so here is activity 30.15, so go ahead and pause the video and give this a try, and then I'll go over the results with you. Okay, so let's go over this activity. So let G equal D6. So I want to remind you that D6 that is the symmetries of the hexagon. And so it has 12 elements, and I just want to remind you that they can be written in the following fashion. So you have the identity, and then you have the smallest rotation, and then if you do the rotation twice, you can do the rotation 3 times, 4 times, and then 5 times. If you do it 6 times, then that's the identity. And then you have the reflection over a vertical line, that's little r, and then you can have little r with each of the reflections, like this. So you get 6 more that have little r. So this is one way to write D6. There's multiple different ways you could write it, but this is one way. Okay, so part A, let us find the elements of the intersection of K and N. So this is pretty easy, it's just the elements that are in both of them. So let's see what is in both of these. Looks like they both have the identity, and they both have little r, and I believe that is the only thing those are the only things they both have. Okay, part B, find the elements of Kn. So remember, this is going to be, we're just multiplying together each, element of these two subgroups. So I believe we actually get all of the elements of D6. So you can do, for example, like, if you do little k equals I, and take all elements of n, or you can do little n equals I and take all elements of k. That gives the following. So that would give you everything that's in either one of them. So that would give you I, that would give you r cubed, little r, r cubed. So that's all the stuff that's in K. And then you would also get all the stuff that's in N. So let's see, I already got I, and then I would get r squared, and then r to the 4th, and then I already have little r, I would get little r squared, and then little r, big R to the 4th. And then we also get, so what are the things that we didn't get yet? We also get r to the 5th, because r cubed times r squared is r to the 5th. So that's an element from K and an element from N being multiplied together. We get just r by itself, because r is equal to r to the, well, let me do it like this. So remember that, let me put it up here. So recall that r to the 6 is equal to I, so r to the 7 is equal to r, okay? So r is equal to r to the 7, and we can get that by doing, let's see, where did my k go? We can get r cubed from K times r to the 4th from N. And then let's see, what are we still missing? So we also get let's see, what else? R cubed. So if we do r cubed from k and then little r squared from n, I don't know if you remember that you can you can commute the little r with the big R if you make the big R's exponent negative. So this is going to be like this. If I move the r squared across the little r, then the exponent becomes negative. So this will be, oh wait, that's not the direction I wanted to go. Let me do it in the other direction. So I move the r cubed across and make that one negative. Then this will be r to the -1, and then that will be r to the 5, because I'm adding 6 to the exponent there because r to the 6 is the identity. And then I think I got all but one of them at this point. So for the last one, I can do r cubed from k and then little r, big R to the 4th from n, and then that will be little r -3, r to the +4, and then that'll be little r, big R. So this is going to actually be all of d6, and then all that is my explanation of why. Okay. All right, so let's do part C here. What are the elements of K mod K intersect N, and to what familiar group is this isomorphic? Okay, so remember that K intersect N is just I and little r. So the cosets here, we're going to take cosets only using elements that are in K. So let me write this. So this will be K intersect N. So let's see, what would be a coset? So of course K intersect N itself will be the first one. And then I can multiply that by another element that is not already in it, but is in K. So let's see, what else is in K? Let's see, r cubed, I think. So we can have r cubed times K intersect N, and then that will give us, I think that actually gives us everything that is in K. Okay, so that'll be it. All right, and then part D, what are the elements of Kn mod n, and to what familiar group? Oh, I forgot to answer that part, didn't I? So going back to part C, to what familiar group is K mod K intersect N isomorphic? So this is a group that has 2 elements, and there's only actually one isomorphism class for a group of 2 elements, and that is Z2. Oops, can't spell class. Group of 2 elements, which is Z2. Okay, so part D, what are the elements of Kn mod n? Okay, so remember that Kn equals D6, and n is written up above, so the cosets of n are, so they're going to be, let me write this part. So the first one will be n, and then we have to think of something that is in Kn or D6 that is not already in n. So you remember that the cosets partition the group. So we have a group of 12 elements, and n is already 6 elements, so we can only have one more coset. That'll be another 6 elements. Okay, and I think we just have to pick something that's not in n, so r will work. All right, so that'll be it. And so again, this is a group of 2 elements. So it is isomorphic. to Z2. Okay. All right, so part E, what is the relationship between these two things? Well, they are isomorphic to each other, since we found that they're both isomorphic to Z2. Okay, so this brings us to the second isomorphism theorem, which basically just states the result that we found in that activity, but in general terms for any groups. So let G be a group, K a subgroup of G, and N a normal subgroup of G. So this means N is a normal subgroup of G. Then K mod K intersect N is isomorphic to Kn mod N. And that's it. So let's look at the proof of that. Okay, so here's the proof. It's actually kind of short, so I was able to fit it on one slide. So we're going to start off by letting G be a group with identity E, K is going to be a subgroup of G, and N is a normal subgroup of G. Then for each little k in big K, we have the following. We can write K as little k as this element right here. So this is an element of K times N. And then if we put that in front of N, we get this coset right here, Kn. So the fact that we're able to write little k as little k times E means that that coset Kn is also in this quotient group right here, Kn mod N. Okay, and so that means that for each element little k in big K, we have one coset in Kn mod N. Okay, and then we're going to define a function phi from K to Kn mod N that is just going to show us that correspondence there. So for each little k in big K, phi just maps that little k to its coset, which is in Kn mod N. Okay, so we're going to show that this phi function is an epimorphism, and we're going to show that it has the kernel of K intersect N. And then what that's going to do for us is it's going to allow us to use the first isomorphism theorem to conclude that K mod the kernel of phi is equal to the, or sorry, is isomorphic to the image of phi, which is going to be Kn mod N. Okay, so all we really have to do is show that this is a homomorphism, or sorry, an epimorphism. So first we'll show that phi is a homomorphism. So we're going to show that it preserves the group operation. So let K1 and K2 be elements of K. Then phi of K1 times K2 is going to be just this coset right here. That's how the phi function is defined. And then we can use the coset operation to rewrite that like this. Okay, and then those are the separate outputs of phi for K1 and K2 if you plug them in separately. So that means that phi is a homomorphism. Now we want to show that phi is an epimorphism, so we're going to show that it is injective. Okay, I'm sorry, rather we're going to show that it is surjective. Okay, so we take some element that is in the codomain. So the codomain here is Kn mod N. So we're selecting a random element from that, which is going to look like this for some little k in big K and little n in big N. Okay, and then we want to show that there is some element in the domain, which is K, that will produce that output from phi. Okay, so what we can do is we can actually simplify this coset right here. We can break it up like this, just using the coset operation. And then this one right here, little n times big N, that's actually just n, because when you multiply the coset by anything that's inside of it, or sorry, when you multiply n by anything that's inside of it, that particular coset is just n again. So this simplifies down to k times n. Okay, and so that means we can definitely find an element that gives us this output from phi, just little k. All right, so little k into phi, we'll get Kn times n, and that's the output that we were looking for. So this shows that phi is indeed an epimorphism. Okay, so finally, we want to use the first isomorphism theorem here, so we need to figure out what the kernel of phi is, and we want to show that the kernel of phi is k intersect n. So let little k be an element of the kernel of phi. All right, then that means that little phi of k, which is equal to kn, since little k is in the kernel of phi, that also means that it needs to output the identity in kn mod n, and the identity in that quotient group is the lower part, which is the n. Okay, so this tells us that kn equals n, so that would mean that little k must be an element of n, if we're able to simplify it like that. So that means that if we take something in the kernel, pardon me, since the kernel is also a subset of k, because k is the domain of the phi map, that means that little k will also be in k. So we started by assuming that little k was in the kernel, and now we've shown that little k is in k intersect n. So this shows that the kernel is a subset of k intersect n. So now we want to go the other way around and show that k intersect n is also a subset of the kernel. So we're going to start by taking an element that is in k intersect n, and then we'll show that that's in the kernel. Okay, so from the fact that a is in k intersect n, that means that a is in n. Okay, so if we plug a into the phi function gives us this coset right here, an, and then since a is an element of n, that's going to simplify to n. And so if you think about it there, what we did was we plugged a into phi, and we got n, which is the identity element in kn mod n. And so that means that a is in the kernel of phi. Okay, so this shows that k intersect n is a subset of the kernel of phi. So it follows then, since we've shown the subset relationship in both directions, this means that those two sets there are equal. And so the first isomorphism theorem then allows us to conclude that k mod the kernel of phi is is isomorphic to the image of phi. And since the kernel of phi was k intersect n, and the image of phi was kn mod n, since it was an epimorphism, then that allows us to conclude this statement right here at the end. And that is the whole proof. I don't think I did a very good job explaining, but I tried. All right, so now let us do another activity where we're going to demonstrate the third isomorphism theorem. All right, so go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go ahead and go over this. So G is D6, and I previously had written out the elements of what that is, so hope you remember what they were. And we're going to find the elements of G mod n, where n is the rotation subgroup of G. All right, so let's go ahead and do that. So n already contains 6 elements, and G has 12 elements. So G mod n has 2 elements, so we're just looking for 2 cosets here. So let's see, we're going to have n, that'll be one of them, of course. And then we just need one more, so something that's not in n would be little r. So we can have little r times n. And then to what familiar group is Gn isomorphic, G mod n isomorphic? So since this is a group of 2 elements, it is isomorphic to Z2. Okay, so part B, find the elements of G mod K and N mod K. Okay, so G mod K, so K is a group of 3 elements and G has 12 elements, so we're looking for 4 cosets this time. So G mod K, let's see. So first of all, there's going to be K itself, and then we just have to start picking things that are not in K. So let's see, we can have R times K, big R times K, and then we can have little r times K. So I think big R times K will give us all of the other rotations, and then little r times K will give us some of the reflections, and then for the rest of the reflections, I believe we can get them by doing little r times big R times K. Okay, so that'll be the 4 cosets there. And then n mod k. Okay, so n mod k is going to be not as many elements. So n is 6 elements and k is 3 elements, so we're only going to need 2 cosets here. So of course there's going to be k itself, and then we just need to pick something that is in n that is not in k. So I think rk will work. So why is n mod k a normal subgroup of g mod k? Okay, so why is n mod k a normal subgroup of g mod k? Okay, so I believe that's just because n is a normal subgroup of g. Follows from there. Okay. All right, so let's look at part C. What are the elements of G mod K mod N mod K? And so what familiar group is that isomorphic? So just to remind you, G mod K was, so that was K, and then it was RK, and then little rk, and then little r big RK, and N mod K was K, and then big RK. Right, so if I'm going to do the cosets of n mod k within g mod k, it's a little bit weird, but n mod k has 2 elements and g mod k has 4 elements, so I'm going to need 2 cosets. Okay, so let's see, g mod k mod n mod k is going to consist of, so n mod k is going to be one of them. So the thing on the bottom is always 1. And then the only thing that I have in G mod K that I don't have in N mod K is the little r element. So I'm just going to do little r times N mod K. And so that'll multiply little r by both of the cosets in N mod K. And that should give me everything. And then again, this is a 2-element group, so it's isomorphic to, Z2. I can't remember if I ever actually taught you guys that all 2-element groups are isomorphic to Z2. We did talk about isomorphism classes a little bit in one of the investigations, and there's only one isomorphism class for size 2. All right, so part D, what is the relationship between these 2 things? So they are both isomorphic to Z2. So they are isomorphic to each other. Okay. All right, so that brings us to the third isomorphism theorem, which tells us that that thing we saw in the activity is actually true in general. So let G be a group, and let K and N be normal subgroups of G, with K being a subset of N. So K is also going to be a subgroup of N, of course. Then G mod K mod N mod K is isomorphic to G mod N. So you can sort of cancel out the mod K part there in a way. So I'm not going to do a proof of this. In the textbook they had the proof as an exercise, and we're kind of getting to the end of the class here in terms of how many proofs I can show you guys. So I'm just going to show you this and not do the proof. Now in the textbook there is also the 4th isomorphism theorem, but I think I'm going to actually skip over that one and just go straight into investigation 31. Like I said, we're getting to the end of the class, and we're kind of crunched for time in terms of what we can do, so I have to kind of pick and choose. So we're going to skip the 4th isomorphism theorem, but if you're really interested in learning about that, it is in the textbook and you can read about it. Okay, so that was the end of investigation 30, and that brings us to investigation 31, which is the fundamental theorem of finite abelian groups. So in this investigation, we're going to learn about how every finite abelian group can actually be broken down into factors of smaller subgroups. So I think just like how I talked about skipping over a proof of the 4th, or some of the proofs and some of the theorems just now, we're also going to skip over some of the stuff in this investigation, like the proofs, and just focus on the most important parts, just in an effort to kind of finish the class and not finish it with like a huge amount of learning of new things. Okay, so let's look at the focus questions for this investigation. So firstly, what is a p-group? In what sense is each finite abelian group made up of p subgroups? And what does the fundamental theorem of finite abelian groups tell us? And why is the theorem considered fundamental? Okay, so let's look at the definition of a p-group. So we're going to be showing that every finite abelian group can be written as an external direct product of smaller groups. And the building blocks in doing this are going to be p-groups. So definition 31.2, a p-group where p is a prime is a group whose order is a power of p. So it could be a group of size 2, for example, or size 4, or size 8, or size 16, or it could be a group of size 3, or 9, or 27, or 81. So groups like that. And the next theorem is going to show us how we can begin to factor a group into smaller subgroups using these p-groups. So let's look at that. Okay, so here's our theorem, theorem 31.3. Let P be a prime and let G be a finite abelian p-group. Let A in G be an element of maximal order in G. Then there exists a subgroup K of G so that G is equal to the, this is the internal direct product of the cyclic subgroup generated by A times K. So the proof of this theorem is really long and technical, so I decided that I wanted to skip it, but it is in the textbook if you're interested. So this theorem here is telling us that we can break G down into a product, an internal direct product, of the cyclic subgroup generated by one of its elements and then some other subgroup. So there are two key steps in applying this theorem. So firstly, you have to find an element that is of maximal order, and then you need to find a maximal subgroup K of G that satisfies this condition right here. So the cyclic subgroup generated by A and K have to have an intersection that is just the identity element. So that's actually one of the conditions for doing an internal direct product. And then once you have that A and that K, then G is going to be equal to this internal direct product. And just to remind you, the elements of that are going to look like this. So A to the M is coming from the cyclic subgroup generated by A, and then K, little k, is coming from big K. So what's interesting about this theorem is that we can actually apply this theorem, we can turn around and apply it again to K itself, and then continue breaking down G into more and more cyclic subgroups. So the next activity is going to kind of guide us through the iterative process of doing that. Okay, so here is activity 31.5. So this will be the last thing that we'll do today. So go ahead and pause the video and give this a try, and then we'll go over it. Okay, so let's go over this activity. So let P be a prime and let G be a finite abelian p-group with order p to the n for some non-negative integer n. In this activity, we will show that G can be written as an internal direct product of cyclic groups. Okay, so explain why we are done if n equals 1. Alright, so if n equals 1, then the order of G is just equal to p, okay? And every group of prime order is cyclic. I can't remember if we ever actually learned this or if we just sort of learned like things that would imply this. I know that we learned that every group of every group of order that's the product of two primes is cyclic, but I don't remember if we ever actually did this. But let me just give you a brief argument for why this is true. Because the Cauchy theorem for finite abelian groups says that if G is abelian with order p and, actually it says with the order n, and p is a prime that divides n, then G contains an element of order p. Okay, so this would imply this element of order P generates a subgroup of order P, but since n equals P in this case, G is generated by the element. I hope that argument makes sense to you. So we're trying to show that G can be written as the internal direct product of cyclic groups, and so if n equals 1, then G itself is cyclic, so it's like just a product of one cyclic group. So in this case, we'll be done. All right, let's look, this is supposed to say B, sorry, it's a typo. So let's look at part B. So now assume that any P group of order less than P to the n is an internal direct product of cyclic P groups. All right, so let's look at part 1 here. What does Theorem 31.3 tell us about G? So that tells us that G is equal to the cyclic subgroup generated by A times K, where A in G is an element of maximal order, and K is a subgroup of G. And then let's see. Okay, so I think that's part 1. And then let us look at part 2. Okay, so if K is the subgroup as described in Theorem 31.3, what can we say about the order of K? Part of the definition of internal direct product is that the cyclic subgroup generated by A and the subgroup K have to only intersect in the identity. So what this means then is that K cannot be the entire group G. Okay, so the order of K has to be strictly less than G. Also, we know that the order of a subgroup always divides the order of a group. So we know that the order of K divides the order of G. So taken together, this means that the order of K must be a power of P, but it has to be a smaller power of P than n. So m has to be less than n. Okay? So then part 3, by considering cases and using Theorem 31.3, complete the proof of the following corollary. So the corollary is let P be a prime and G a finite abelian P group, then G is an internal direct product of cyclic P groups. Okay, so we have most of what we need here to do this by induction, because this this assumption right here, this is like a inductive assumption, and we already did the basis step on the last slide. So I'm not going to write out the whole proof from scratch, but I'll just like kind of finish up the argument. So by the inductive assumption, K is a P group of order less than P to the n. So K is a product of cyclic P groups. I should say an internal direct product. Oops, I misspelled groups. Grops. Okay, so I'm going to say that k equals, like, I don't know what I should call them, like maybe a1 times a2, like this, times dot dot dot, times, I don't know how many there would be, I'll just call it j, I guess, for some j. Okay, so then g is going to be equal to, remember g was a times, or cyclic subgroup generated by a times k, so this will be a times a1 times a2, and so on and so forth. Okay, and that's it. All right, so that's it for today, everybody. We'll finish up with section 31, investigation 31 next time, and then I think I'm probably going to give you guys Friday off to give you a little extra time to work on your exam and catching up on your homework and so on. So let me know if you have any questions or you're having any trouble with test, homework, exam, anything like that. I'm happy to help you guys out more than would probably be possible in a normal semester. Just send me an email. Bye-bye.